G'day, Richard Marr here again from Mars Classes. This episode we're going to be looking at Kepler's laws of planetary motion. Now, to put it in context, we've got to recognise that when Kepler was around, society and the church believed in a geocentric view of the universe. Geocentric meaning the Earth was centre to everything and everything else orbited around it. But through observations and mathematics, Kepler and contemporaries were responsible for changing the view to a heliocentric. Helio coming from the Greek word for the sun, which said that the planets actually orbited the sun that was the centre of our solar system. And through his observations and mathematics, he developed many laws, but he developed three laws which are recognised now as Kepler's laws of planetary motion. Now, the first law was that he recognised that when things orbit, they aren't actually orbiting in circular paths, but they are orbiting in ellipses. Now, when we look at ellipses in textbooks or websites, we do see this very exaggerated ellipse. You'll actually find that when you look at the ellipses of planets, that it's pretty close to circular, but it is not exactly circular. It is an elliptical orbit. And also, we notice that the terminology there, the semi-major axis, is the average distance between the sun and the planet. So you could think of that as the radius of a circular orbit. His second law is an interesting one because it says that if you connected a line between the planet and the sun, during equal intervals of time, equal areas would be swept out by the planet as it moves. So an upshot of that is that when planets are closer to the sun, they're moving faster than when they're further out. Now, that's is supported by the law of conservation of energy, because when they're closer to the sun, the potential energy will be different to when they're further from the sun, and therefore the kinetic energies will also be different at those different places, because the sum of kinetic and potential energies will be the same in all locations. His second law also can be sort of explained without going into calculus, but sort of demonstrated if we consider 2 points on the orbit, the perigee and the apogee. Now, the perigee is the point closest to the sun, and the apogee is the point furthest from the sun. Now, if we were looking at those 2 points and recognise that the radius or the distance from the Earth or the planet to the sun at the perigee is smaller or shorter than the distance from the planet to the sun at the apogee, and I've represented that with a small r and a capital R. When we look at the sun itself, it is called Sol by the Latin or the Romans. The Greeks did call it Helios. So when we're saying perigee and apogee, we're talking about any satellite. If we're talking about things going around the sun, we actually say perihelion and aphelion. So if we're looking at those two radii, they are going to be different distances. And when we consider those two things there, if we look at the velocities at those places, we've said that it's going to be moving faster closer in at the perihelion than it is at the aphelion. So when we look at those two velocities, if they're measured in metres per second, then 1 second after the planet passes the perihelion, it will have travelled v metres, and 1 second after it's passed the aphelion, it will have travelled a little v metres. So you'll see that the distance travelled at the perihelion in 1 second is greater than the distance travelled at the aphelion in 1 second. And when we look at those distances and the radii, or the distance from the sun, we'll see that those two distances are two sides of a right-angled triangle. And if we look at the area of that right-angled triangle, that would represent the area swept out by the planet in 1 second of its orbit. Now, Kepler's law states that area swept in 1 second after perihelion would be the same as the area swept 1 second after aphelion. So let's just check that mathematically. We know the area of a triangle is half base times its perpendicular height. So if we substitute in the base as being the velocity and the perpendicular height as being the radius, we get half big V times little r equals half little v times big R. Cancel out the halves and we get big V times little r equals little v times big R, and we can get a ratio there that the ratio of the velocities is the same as the inverse ratio of the distances. So that's what we get from Kepler's second law. Kepler's third law is one that says that if you look at the square of a planet's orbital period, it's proportional to the cube of its semi-major axis. So that sounds like a mouthful, but what we're saying is r cubed, or the distance that it is from the central point of its orbit is proportional to the square of the period. Now that goes for all planets that orbit the Sun. So what we get, the upshot of that is the further the planet is from the Sun, the longer its period would be. So see if we can verify that with some simple mathematics. So if we're looking at the Earth, for example, and that is looking at it from above, it looks quite circular, that orbit there, because it is really quite close to circular. But I'll point out something here. The sizes of the planet to the Sun is not to scale, and the size of the planet from the Sun is definitely not to scale either. So let's just have a look at this now if we view it from sort of the side. We know that the Earth has a particular velocity. If it was a circular orbit, that velocity would be equivalent to 2 pi r on the period. Now, if it just had that velocity and there was no force acting on it, it would be travelling in a straight line. But we know it's travelling around this elliptical or nearly circular orbit. So there must be some force acting on it to change its motion, because it's Newton's laws tell us that. And in this case, it's got a near circular orbit, so the force would be a perpendicular force to the direction of its motion. And that force is providing a centripetal force, and we know the value of centripetal force will be mv squared on r. But what's giving that centripetal force? Well, it's the gravitational attraction between the Sun and the Earth. So we can express that as gm1 m2 on r squared, and they are going to be equivalent. Now, if we simplify this down, we can cancel out the mass of the Earth and the radii, and we get the v squared equals universal gravitational constant times the mass of the Sun on the radius. But we've set up above that the velocity is 2 pi r on t, so v squared will be the square of 2 pi r on t, which is 4 pi squared r squared on t squared, equals the gm mass of the Sun on the r. And then we can just do some cross multiplying, and we'll get that the period squared is equivalent to 4 pi squared r cubed on universal gravitational constant times mass of the Sun. Now, we know that 4 is a constant value, we know that pi squared is a constant value, we know that the universal gravitational constant is a constant value, and we know in this instance that the mass of the Sun will be constant. So we actually get that some constant value times r cubed is equal to t squared. So that's a bit of verification for Kepler's third law. It's not entirely accurate because it is not a circular orbit, and there's a few other things to consider when we're looking at planetary motion. So we do need to correct a few of these things, and mathematically that has been done. So for example, the Earth and Sun actually rotate about their common centre of mass. The Earth doesn't, because they're both attracting each other due to gravitational attraction. So we know the centre of the mass of the Sun is in the geometric centre of the Sun, but the centre of the mass of the Earth and the Sun system is somewhere away from the centre of the Sun, but it's still within the Sun. It still corresponds to a point within the Sun. Now, the interesting thing about this is the whole system will orbit around that blue spot, that centre of mass of the Earth-Sun system. So what you will get, and if you look at viewing from above when the Earth is orbiting the Sun, if you were just looking at the Sun from a distance, it would be seen to be wobbling or rotating around some point. Now, when we look at distant stars, we can use that as some evidence that there is some planet orbiting it. So that's one of the mechanisms we use to detect extrasolar planets. Okay, that's a very brief look at Kepler's laws. There's a lot more mathematics involved in it, but we're just treating it at a very simplistic level here today. So until next time, I'll see you then. Bye.